organizers for having me. I would like to preface this talk by saying that this is work done by a student in our group, but because he had to present this at the Numerical Relativity Conference, he sent me instead to do his talking on his behalf. But I also like to just highlight some of the collaborators here, including Tjonnie. And I want to talk about, indeed, our code that we have to do full Boltzmann solving. So as we saw in the let's say the lecture this morning, the neutrinos play a pivotal role in core collapse supernovae, and so it's very important to include them in the simulations. And so if you look at the actual equation that you would like to solve, if you want to include everything, this is the Boltzmann equation, which is a 3 plus 3 plus 1d, so x, p, and t. And here is the equation itself, where I don't know whether there's, okay, there's more or less a pointer. So where f is the neutrino distribution. And so what happens usually is that, this is a very, large kind of equation to solve. And so often we make approximations, moment-based ray tracing, which are computationally efficient. But the question is, what is lost when making these approximations? What are the effects on the system and on the emitted signal? And this is where a Boltzmann equation solver comes in, so that we can at least study these systems and see what are the differences that when we do the simulations in approximations or using the full Boltzmann equation. And so to solve the equation is all about tracking the change of f, right? This is the neutrino distribution along the geodesic, and then comparing that to the collisions, so the interactions that happen along the geodesics. And to do so, it requires explicit choices. In this case, both the phase space coordinate system and the reference frame in which the momenta are defined. And these choices actually make significant impact on the accuracy, efficiency, and also on the treatment of neutrino matter coupling. And so I want to spend a little bit of the talk talking about some of the choices that we've made, how that is different from what other people have done in the literature, and then hopefully towards the end, I'll show you some example cases where we do run the simulation. So the first thing that we need to do is we need to complement the space with the momentum. And in our case, we have a momentum in the spherical coordinates. So this is your usual, your usual spherical coordinate system here. And one thing that is important then is the choice of reference frame. And here you can have several options. One is using the local orthonormal frame. This is, for example, that is done in Okayo et al. But what we do is we do the local co-moving frame. And I'll explain a little bit where the differences lie and also what are the advantages of each. So, for example, if you have a fluid where there's a large velocity gradient, then in the orthonormal frame, the momentum advection is easy. So this is what is shown in orange, where there is no advection of the momentum, right? It remains nice and steady, assuming in this case massless neutrinos, and that the fluid is completely decoupled from the neutrino. Of course, in the co-moving frame, things become trickier because you have a large sudden change, right? In this case, in a very small span of time, there's a large change in the velocity. And so if you do this in the co-moving frame, if you do this in a co-moving frame, you need to be able to resolve this and take into account the, if you use the co-moving frame, that then your momentum of your neutrinos changes from one to the other side. But it's not all bad, right? Because what we now lose in terms of being in a co-moving frame and having to resolve these velocity-dependent terms, we gain back in the interaction terms, because the interaction terms are all computed in the co-moving frame. And so if you are actually doing your calculations in the orthonormal frame, you need to go back and forth between the two, whereas in our case, we can simply stay in the co-moving frame and we can really do the interaction opacities, interaction rates, etc., in the co-moving frame. Okay, so the system of equations that we solve is the conservative form, so that we conserve the number of neutrinos, and of course our curvilinear coordinates for the momentum. And so if you write this out, you can kind of see the the framework that Cardall et al. Set out. And in that case, we also use the reference metric formulation for the three metrics. So ultimately, this then leads to a 1 plus 6D conservation equation, which we've implemented into Gmunu. So we've extended Gmunu for 6D finite volume method. In this case, Gmunu is our own in-house GRMHD code with advanced microphysics included.
What is the metric here?
Sorry?
You use some metric, gamma, and what metric do you use?
Okay, so in this case, what we solve is the XCFC. Yeah. So, okay, so some of the extra care that are required, I've talked about the coordinate system and the reference frames. Another thing that is a little bit tricky, especially when you're doing this in the co-moving frame, is also things like boundary conditions, right? Where for the fluid, if you're in a boundary condition, the velocity is simply a vector. You can just flip the vector. But in the case of, when you need to keep track of the neutrinos, suddenly it's no longer just a flipping of the sign. You're actually in a different point in your momentum space. So you need to keep that tracking of where in the boundary conditions in order to make things run properly. Finally, also, the discretization also means that we have to discretize the flux. And so the equation that is shown here, for example, we need to ensure that this is true in a discrete limit where even terms that should cross-cancel are actually cross-canceling when you discretize things. Okay, so let me not just talk about the implementation, but try to convince you that the implementation is moving in the right direction. And so one of the things I talked about is indeed in the co-moving frame, we are sensitive to velocity gradients. And so the question is, should we be concerned in this case? In particular, when we discretize the equations, are we sensitive to the local fluid velocity profile? So in this case, I'm going to do something very extreme, right? I make a very extreme velocity gradient, and I'm going to see, can I actually resolve all this information so that we set out to show that our code can accurately track what is shown here in the black line here. And you see two different setups, one without adaptive mesh grid and the other one with. And indeed, you can see for the same number of bins, provided we do use the adaptive mesh grid, we are getting fairly well up there for a discontinuous velocity profile. In this case, I should say, despite the difference that you do see here, this example is fairly extreme. And so for the shocks in core collapse, we don't expect such extreme cases. So we're fairly confident that provided we use the adaptive mesh grid, that we have this, well, to a certain extent under control. Okay, moreover, in dense environments, the neutrino transport itself can become diffusive. And so we also implement a correction when the mean free path of the neutrinos cannot be resolved properly. And again, here we show that for large scattering opacity, our results, our simulation, follow the expected black line here. And so the corrections are also doing the work in the diffusive limit. Okay, another test that we've done is to simulate a homogeneous radiating sphere, which is a toy model for a hot neutrino. And you can see here on this figure, you can see both the analytical, which is in black, and then several different simulations for different levels of opacity. And so regardless whether it's optically thin or thick limits, we are resolving the proper behavior. Okay, I come to the last part that I want to show, because we've actually started doing supernova simulations. In this case, this is a 15 solar mass progenitor with a relatively soft equation of state. What is important is that we actually couple this to a weak up interaction table, which is kind of our most advanced microphysics module. We use 20 bins in the momentum, 10 on the angular side, and we simulate from collapse, bounce to the expanding shock. Now, if you compare the M1 versus the Boltzmann, you do see some differences. For example, here, which we think may be due to boundary conditions, but also there are other parts where we see some deviations. This is in the velocity profile. We can see the similar things in both the temperature and the electron fraction. This is some behavior that we are currently looking into, try to understand, what exactly is going on. But at least I wanted to be able to show you the first kind of supernova simulations we've been doing using this code. And then finally, basically to conclude, we have now a multi-dimensional relativistic full Boltzmann solver in Gmunu. So far in benchmarking tests has shown good agreement, what we expect. A paper with the full details and test in preparation. And finally, we've been just awarded some modest supercomputing time, some few million CPU hours to really start doing a set of 2D simulations, supernova simulations, using all of this physics that we have now. So that's it. Thank you very much.
Can I ask Martin? Thank you very much.
Behind you.
Okay, thanks. Hi.
I was wondering, Boltzmann solvers always have a big problem with the diffusive limit. So do you have done tests, how to which accuracy, numerical precision you are matching the diffusive limit in the high temperatures and high density regime?
Some of the tests that I've shown is really the first set of tests that we've done. So we haven't really looked at the full suite. We are looking into it, but yeah.
That could very well due to that.
It could well be. It's something that we're still trying to see if it's a bug or indeed the diffusive limit.
Well, let's go in order to spatial order.
So it's okay. So just one quick question. So you mentioned like this velocity discontinuity.
Yeah.
I think this energy advection.
Yeah.
This characteristic velocity is infinite. So you mentioned like AMR kind of like this treatment, but if we have such again like a very sharp velocity discontinuity, delta t, I mean time step width should be very, very small.
Sure. Yeah.
So how do you overcome this difficulty?
We run a very long time.
Okay. Okay. Very short time delta t. Okay.
Yeah, but that is actually one of the things that we're hitting now is that, especially when these very big steps, our time resolution that we need to run becomes very, very small.
Okay.
It's one of the things that we're trying to address.
So you said you had 10 angular bins.
Yeah.
Are these really just discrete, or are you using some set of basis vectors like discrete ordinate or something like that?
No, for now it's just.
Because I think that also might help with going from the diffusive to the free streaming.
Okay.
Thank you. Very exciting work. I imagine these must be incredibly computationally expensive compared to, M1 approximations.
Sure, very much.
How can you give me an estimate? And are there plans like when can we see the first full second, full transport equation? Are there any opportunities to accelerate this on GPUs?
Yes. No. Okay, so to give you, we tried to estimate to do like a 2D one. If we don't do any further speed ups and things, we're looking at maybe a billion CPU hours. We'll have to see how we can speed things up. GPU, same thing. It's directions that we want to go into, but we need to find the time and space to do that. For now, we just wanted to have the first real implementation before we start thinking about speeding it up on heterogeneous computing and stuff, but it's on our radar. Yeah. But we do hope to do some, 2D stuff already where even starting with M1, freezing it, and then also having intermediate periods where we turn on the Boltzmann solver just to already start making comparisons. But we also hope to do some full Boltzmann stuff with this modest grant that we have. Yeah.
This will be a very quick question. On this slide, you show the discontinuity and the velocity.
Yeah.
What is the magnitude of the velocity discontinuity here?
Ooh, I'll have to look it up for you and get back to you. Yeah.
See any of them? That's thank Tjonnie again. The next presentation is to be given by BOGL Alcohol on focal super